Hello all, this is part 2 of the hands-on computer vision tutorial where I will explain you the code. All the theoretical concepts and methodology has been discussed in the previous video. If you have not seen that yet, please go look at that first to have a good understanding about the project. We will be following the exact same steps to write the code as discussed in the last video. Let me explain you the code and demonstration of the system. So for this project, we have worked on Google Colab to leverage the GPU power. Free tier of GPU offers Tesla K80 GPU with 2,496 cores and 12 gigs of GDDR5 RAM. So first and foremost, we need to install the libraries, few dependencies. So as we can see here that we are installing PyYAML, and the most important one is PyTorch, since Detectron 2 is completely built on PyTorch, and the version that is much supported is 1.7. So we are installing PyTorch with the version of 1.7 along with the Torch Vision. So as of now, the current PyTorch version is 1.10, but the Detectron 2 is much more compatible with 1.7. So next up, we can import the library and we can see the Torch version, which is 1.7. Next up, we need to install the Detectron 2 framework using pip and using this following link. By running this cell, we are going to install Detectron 2 with all its dependencies. The next up, we are going to import Detectron 2 and some very common libraries like the NumPy, which is a statistical library, the CV2, which is a computer vision library to manipulate the images. And then we have the matplotlib to plot some graphs and something. Also, we are going to import some of the common utilities that were downloaded along with Detectron 2, which is the model zoo, which is a neural network API. The next is default predictor, which we are later going to use to predict our output. Then we have the configuration. So by using this, we can have the by default configuration for the model zoo. Next up, we have the visualizer. So in order to visualize our images, we are going to use this library. And then we have the metadata catalog, which is going to be used to register the dataset, which we are going to see later. Next up, we are going to mount our drive. So which we can, by running this cell, we are going to mount our drive, which we can see here. But if I go to my drive, this is just taking me to my drive. And inside that, I have a folder called image segmentation. So we have imported all our training, testing, validation datasets into the Google Drive, which we can see here, test, train, and validation. We can also just have a look what is in our Google Drive. So we can see that we are going to the image segmentation folder of our Google Drive. There we can see we have the test, train, and validation datasets. So if we just open the training one, we can see the images along with all the JSON files. And for every image, we have a JSON file. In that JSON file, we have the annotations of that image, which is previously explained by my colleague Gavin. Also, we have the test dataset. So as we can guess that we don't have the JSON files because these are all the dataset that our model is going to predict. So no JSON files for this. And then we also have the validation dataset along with all the images, along with all the JSON files. So in order to check the accuracy and efficiency of our model, later we are going to use this validation dataset. So coming back to the code, moving forward, we have written this method called getIndoorDicts, which is going to tell the Detectron that how we want our data to be trained. So firstly, we have defined all the classes that we have, all the labels that we have in our images. And next up, we are going to take all our images along with the JSON files. And this method is going to return us the bounding boxes along with the segmentation across all these images, and also the labels for that particular image. And all these annotations on that particular image is going to be written by this method, and which we are going to later see that how our training data looks like once we are going to use this function on them. The next step is to register the dataset. So we are registering the dataset using the metadata catalog. Registering the dataset means that we are telling the Detectron from where it should get all these data. So we have used this for loop for training, testing, and validation datasets. So metadata catalog.get, it means that for that training dataset, it's going to store indoor/train will contain all the images, the training images. For that validation, it's going to be indoor/validation. And similarly, for the test, it's going to be indoor_/_test. And now after this one, we are going to register the dataset. And next up, we are going to access the dataset by using the command .get indoor_train. So before training, we have written the code for showing the images, that how our image looks like. So as we can see that we are using this get indoor dict, the function that we created, onto all the training data. We are using this for loop so that we can see all the images that are in the train and applying this function on all those images. So upon applying this function, we can see our data set now looks like this. So we have this iron is going to have the mask, also the bounding boxes along with the labels. So we are just showing here some of the random images for all these things. So these are the training data set. Next up, we are going to train the model using the default trainer and get config. So Detectron 2 offers many model architectures for object detection in its model zoo. So first of all, we need to import model zoo. And for instance segmentation, we have selected weights for the faster RCNN. So we are importing this mask faster RCNN and we are initializing random weights to it. So for the training dataset, we are going to pass the indoor_train. As of now, we are not interested in testing. So we haven't passed any parameter to this. Next, we have to tune the hyperparameters. So as we can see that images per batch. So we have selected 2 images for 1 batch. The next one is the learning rate. So we have selected this learning rate after applying many different random learning rates, and we found out this is the most efficient one. If you're going to select the larger learning rate, so it is highly likely that it's going to miss the global minimum. And if we select the lower one, lower value, so the training is going to take much longer. Next up is the iterations, which in machine learning terms are also known as epochs. So we have selected as 4,000, which we believe we also have selected different values for this. And 4,000, we believe that it's going to be the optimal value for the training ones. Next up is where we are defining the training classes, that how many classes we have in our data set. So upon running this cell, it's going to create an output directory. And in that output directory, our trained model is going to be saved. So also by running this cell, we can see that we are using this CNN model. So all the by default parameters, we can see for the CNN model, that input layer is going to be 256 by 256. The kernel size is 1 by 1. We can see the strides. And there are also some of the hidden layers. And if we go down, we can also see the activation function that we are going to be using is by default ReLU. And also here we can see all the instances of the images. So we have these, as of now, we can see that these are the 11 classes for each class. We have these images. Sorry, my runtime is disconnected. Let me just quickly connect it again. Yeah, so the total instances, we have 911 from all these images. So we believe that this training data set is sufficient enough to give us decent accuracy. Next up, we are just going to train the model. So upon running this, we can see that initially on the 19th iteration, the total loss is 3.567. And as we are increasing the iteration, the total overall loss is getting decreased. And if we just see on the 4,000 data, 4,000 iteration, we can see the total loss, which is significantly decreased from 3.5 to 0.1655. And the total training time for this data set is somewhere around 2 hours. So even with utilizing the GPU power and efficient Google Colab, still it's taking us around 2 hours to train the model. So once the model is trained, you can see the model weights, which is saved by the name model_final.pth. So now once this model is trained, you don't need to retrain the model every time. We can just take this and we can load the model and then we can just make the inferences. So the next step is to load the model. So we can see that the output directory, we are going to load this model. And this time we are going to use this test data set. So indoor_test, and we are using the default predictor along with all the predefined configurations to predict the model. So in order to make the inferences, we can see that we are using this test folder. So we are all the images that are going to be in the test folder. By using this for loop, we are going to perform the prediction, and using this visualizer, we can see all these images. So I can just quickly run this one because this is going to be the output. So we can just see the outputs. Yeah. So we can see that the model has started its prediction. So we can see that it's these are the chairs. The model is predicting the chairs pretty well. It's the confirmation is 99%. Probability that it's a chair. Next up, it's another chair. It's you can see that these are the lamps. So 93% lamp, 94% probability that it's going to be the lamp. Further, we can see that these are the cups. These are also the cups, but the model didn't predict this cup. So this is the iron, 97%, 98%, and the output is going to be in this very form. So these were the images taken by my cell phone or the camera. So anything that is going to be present in the test folder is going to be predicted. It's going to predict all these classes. So we can see that the accuracy is pretty good as of now. So these are in this format, we are going to have this test data.